I'm going to demonstrate how to get fast Fourier transform. We have already discussed about the dependence of the different type of chaotic dynamical behavior of the Duffing oscillator with the control parameters. So what we will do, we will generate time series either x or y as a function of t, and from that time series we will use the graphical software to do the Fourier transform, and from the Fourier transform we will be able to uh, find out whether the system is periodic or chaotic. So let us start with the my program is Duffing.4, so I will compile it. So I will ignore this warning. So first is omega square, which is minus 1.0. Second input is beta, is 1.0. Third is alpha, damping constant 0.5. Fourth is the external frequency, which is 1.0, and the frequency is, so I will start from the lowest external amplitude, which I can set 0. So you will get stable point here. So I will put 2 lakh points. So what I did, my time step is 1 by 100 of the time period of the external source. So let us start. So Duffing Fourier transform f0 dot dat. So I will plot it, and then I will use the module in the graph, the XM grace, to find the Fourier transform. So as you see that it's stable, it goes to there is only one point. So I will do the Fourier transform of this, take index and this as a frequency. So I will take the magnitude, and then so Fourier transform I have done. So okay, so I will, since it is not visible, so I will take the log of this. So solute evolute expression, so this I will write as ln y into y, that is the square of the amplitude divided by ln 10, so it is in log of 10. So my new value is ln of the coefficient square by ln 10, so it is written as log of 10 square. So let us draw it. It's a minus 20. Okay, since it's 0 to 100, so as you see that there is a peak, a sharp peak at this x equals to 0 here. So the frequency is 0, hence it's a stable point. So this you can see clearly. बंद करना है. Okay, so now let us take different point 1.0, then 1.0 beta, then alpha 0.5 and omega 1.0. So I will change my f. I will put 0.33 where I will get period 1 behavior, and this is Duffing Fourier transform f33 dot dat. Let us plot it. So you can see it's a period 1, and because this time series shows only one period. So do the Fourier transform of this Fourier transform. So you take the magnitude as a function of frequency and do the Fourier transform. Close. So we have to increase the number of data from 20,000 to 2 lakh, right? And then you hide this because we want to see only Fourier transform. So this Fourier transform you can see, but since it is spikes, very few spikes, so we will take log of this as done in the book. So we will then evaluate expressions. So this y we will write in a new form, that is ln y into y upon ln of 10, and then we'll hide it. So now it's a log of this, so we'll start from minus 20 to let's say 5, and then okay, so you can see that okay, let us 0 to 2. So this small you can ignore because its strength is very small as compared to this. So you have this 0.16, then one is 0.32, then 0.48. So this is the fundamental frequency, and the integral of multiple frequency you get various spikes of reducing intensity. So it's a period 1 because you have only one frequency, others are just integral multiples of the fundamental frequency. Okay, so now we will change the parameter f further, so keeping other parameters same. So we'll take 0.35 where we got period 2, 2 lakhs points I'm selecting for better statistics. So this is Duffing Fourier transform for f35 dot dat. Let's do the Fourier transform. So we have to increase the number of points. It's 20,000, so I will make it 2 lakh. So it looks like this, but it's period 2, so it's not apparent here. So we will do the Fourier transform. So we will go like this in terms of frequency. We will remove this because we don't want to see the time series, we want to see only this, but in a different form. So I will do another transformation from this. So I'm rewriting the Fourier coefficients in terms of ln, a log of 10 of square of the Fourier coefficient, where I can see various spikes clearly. So let us see it. Okay, so you can see, so I can remove this part because I don't want, so you can hide it. So you just take 0 to 1, just only spacing you can take 0.25, Okay, so you can see the one is at 0.80, the another is 0.16, then 0.23. So number of spikes are doubled, and when you see the previous case, number of spikes were half of this, so it is period 2. Okay, now we will see the chaotic case. So we will change our parameter f so that the dynamics is chaotic. So as you know, it is 0.365 lect. So Duffing Fourier transform f 65. So let us plot it. So it's chaotic in nature. You can see from the time series. So the equivalent information you can get from the Fourier transform. So I will do the Fourier transform of this. So I will select my x as a frequency, do the Fourier transform. So I will increase the number of points, say for 20,000. So take 2 lakh drawing path length. So you remove it first because you don't want to see the time series. Now you can see this broadband, but it's not apparent here. So we will do one more transformation. So I will rewrite this coefficient in terms of new value, which is log of 10 of log base of 10 of the square of the Fourier coefficient. Okay, so you don't want to see it, so you remove it, hide it, and let's say, and then since it is a negative log of this, so minus 20 to say 1, the interval of let's say 4. Okay, so you can clearly say, so let us say 0 to 1, you can put it like. So you can see that it's a broad band, and mostly the Fourier spectrum is broad, and there are very less spikes you can see, but they are the unstable periods, and the dominating frequencies of unstable periods can be identified from the spikes. But the bottom line is that the Fourier transform is broad as a function of frequency. Okay, so this is single band. Now we will go to double band before we wind up. So omega square is minus 1.0, beta is 1.0, alpha is 0.5, external frequency is 1.0. So we'll take 0.42 f where we have double band chaos. So I will take 200,000 points. So Duffing Fourier transform of f or 2 that DFTF. So it's a double band chaos because it goes -1 and +1 also. So I will increase the maximum drawing path length, make it 2 lakh. Okay, so you can do the Fourier transform as we have done earlier. Yes, function is frequency. Don't want to see it, so you can hide it. So you do one more transformation. You're writing this coefficient in terms of log 10 of coefficients. square. So this is ln y into y upon ln 10 y. Now you do it from -20 to 1 with spacing of 5. Okay, maybe. Okay, so okay, so you can hide this as we have a better resolution, so you can see that it's completely broadband chaos. Okay, so you can clearly see. Okay, so in this video I've use the module of XM Grace to find the fast Fourier transform of various time series calculated at various control parameter, and from that Fourier spectrum you can easily quantify the periodic behavior as well as chaotic behavior. Thank you.